Hello everyone, in this lesson we will be studying the graphs and properties of exponential functions. In the last class, we learned a new exponential function. Let's review the concept of exponential functions and the characteristics of their analytical expressions together. The general function y is equal to the power x of a is greater than 0 and a is not equal to 1, which is called an exponential function, where the exponent x is the independent variable and the locality is r. Based on your experience in learning functions, please analyze what the research content of our lesson should be. In this lesson, we will learn about the graphs and properties of exponential functions. What are the properties of functions? The monotonicity and parity of functions. In Chapter 2 on the concept and properties of functions, we learned about power functions. What steps do we need to go through to study the properties of exponential functions? We can roughly divide the study of specific function properties into 3 steps. First, draw a graph of the specific function, observe the function graph, and summarize the properties of the function. Then, by observing and comparing different function graphs, we can summarize their common features. Today, we learn about the properties of exponential functions in the same way. Our current task is to draw a graph of the exponential function. We have found a problem where the base a of an exponential function is uncertain, so we need to determine the value of a and find a specific exponential function. What is the value of a we choose? We can study the graph and properties of the function y to the power x where a equals 2. Before drawing a specific function graph, please analyze our preliminary understanding of the graph and properties of the function y equal to the power x of 2 based on the definitions of exponential operations and function properties. Please talk about your gains. Some students say that from the concept of exponential functions, we can know that the definition of a function is r. Very good, but what about the range of values? The value range may be from 0 to a large open range of positive poverty, but it is not very certain. What can you be certain of? Saying that the power x of 2 is equal to 0 and that the power x of 2 is less than 0 is always unsolvable, so the power x of 2 must be greater than 0. What we can confirm is that the exponential function y is equal to the power of 2x, and its graph must be above the x-axis. Okay, is the value range from 0 to positive infinity open range? We can use images for further analysis. Do any students have a preliminary understanding of the nature? We found that the parity of functions can be concluded from a definition perspective. We consider 2 special cases, where the power of 2 is equal to 2, and the negative power of 2 is equal to half. We found that 2 and half are neither the same nor opposite numbers, so we conclude that functions do not have parity. What about monotonicity? It is difficult to draw a conclusion from the perspective of defining monotonicity. However, comparing the power of 2 to the negative power of 2, we should find that this function is not a subtraction function. What about its monotonicity? We can draw an image and further study it. So below, please draw a graph of the exponential function y equal to 2 on the x side. We should be using the dot tracing method, but what are the requirements for selecting the value of x in the dot tracing method? It is best to have positive values, negative values, integers, and decimals. Here, I have provided a logarithmic table for x and y and plotted the graph of the exponential function. Please combine our analysis of the property of the exponential function y being equal to 2 on the x side when drawing the image. After drawing the image, explore the properties of the function. This is the graph of the function we created using the tracing method. What properties can you obtain from observing the graph? What are some of the properties we have just explored that can lead to clearer conclusions? We observe the graph and find that the graph of the function shows an upward trend from left to right. The function has no maximum or minimum value, and its range of values should be between 0 and positive infinity. The graph of a function is not symmetric about the origin or the y-axis, so the function does not have parity. Then let's look at monotonicity again. Observing the graph shows that the function is an increasing function, so our previous understanding has been verified one by one. Okay, so now we have completed the study of the graph and properties of the function y to the power x of 2. So, everyone, what should be our next task? Next, we will investigate whether other exponential functions also have such graphs and properties. So we need to select another exponential function for research. Please draw a graph of the exponential function y equal to half the power of x and observe the graph to explore the properties of the function. I'll take a look at the results. On the left is the graph table where everyone has created an exponential function y equal to half of x squared. On the right is the property we are exploring. Let's take a look at the properties of exponential functions together. Its definition is that the entire range of real numbers is from 0 to positive infinity, and the monotonicity is a decreasing function. Since parity does not exist, it is not listed in the table. By observing the properties of this function, we will find that its locality and range of values are the same as the x square where y equals 2. But its monotonicity is not the same. Do the properties of these two functions give us a hint that we need to classify and study the graphs and properties of exponential functions. Before answering this question, please answer me this question. How do you draw the graph of the function y equal to half x squared? Please describe your approach and the basis for it. Okay, some people say that I used the point drawing method, and the points I drew are the same as the ones I selected for the x squared where y equals 2 just now. Is there any other way? Some people say that I am using a graph with more symmetry. Please explain the basis for your actions. Because y is equal to half the power of x and can be simplified to the negative power of 2, points x, y, and point negative x, y are symmetric about the y-axis. So based on this symmetry, we find that any point p, x, y on the graph of the function y equal to 2 to the power of x, with respect to the y-axis symmetry point p1, negative x, y, all lie on the graph of the function y equal to half of the power of x, and vice versa. This indicates that the graph of function y to the power of 2x and the graph of function y to the power of half x are symmetrical about the y-axis. Therefore, we can use an image with y equals 2 to the power of x to directly draw an image with y equal to half of the power of x. Let's take a look at the basis for using symmetry to draw graphs. When 2 and a half are reciprocal to each other, the graphs of these two exponential functions are symmetric about the y-axis. Can this symmetry be extended to general exponential functions? The answer is yes. Let's study two exponential functions. One is y equal to the power x of a, and the other is y equal to the power x of 1a. Of course, a must be greater than 0 and a is not equal to 1. It is said that because y is equal to the x power of 1a, it can be reduced to the negative x power of a. According to the same derivation process, we can draw a conclusion. The graphs of two exponential functions with reciprocal bases are symmetric about the y-axis. Based on this symmetry, we can use the graph of one exponential function to draw the graph of another exponential function. So, everyone, how does this symmetry help us study the graphs and properties of exponential functions? Based on this symmetry, we can classify the graph of the exponential function y equal to the power x of a into two types according to the value of the base a greater than 1 and a greater than 0 and less. Please recall the two functions we just studied, which happen to be functions of these two types. Let's review the properties of these two functions. This is the graph of two functions we have created, with y equal to the power of 2. Its definition is that the R-value range is 0 to positive, infinite, and the monotonicity of the open interval is an increasing function. Y is equal to half the power x, and its domain is defined as R ranging from 0 to positive infinity, with monotonicity being a decreasing function. Of course, neither of these functions has parity. Our next task is to investigate whether those two types of functions have the same properties as this function. Let's first study the graph and properties of the exponential function when a is greater than 1. Will this type of function need to be further divided? This question is not easy to answer, right? We still need to look at the research results of specific functions before drawing conclusions. Now let's draw two graphs of exponential functions. Please draw graphs of exponential functions y to the power of 3 and y to the power of 4. Observe the graphs and explore their properties. Okay, I will place the image in the same Cartesian coordinate system. Please observe the images and explore their properties, while also seeking similarities between their properties and the function y equal to the power x of 2. Let me show you the results. We found that the locality of both functions is in the R range, ranging from 0 to positive infinity, and their monotonicity is an increasing function. These properties are the same as the x power of function y equals 2. At the same time, through the image, we discovered a new feature that these two functions have a common point, and the coordinates of the common point are 1. And the points 0 and 1 are also on the graph of the function y equal to 2 on the x side. So, now we ask, can the properties summarized by these three functions indicate that all exponential functions of this type have such properties? Please think about this question first. Let's study another type of exponential function. When a is greater than 0 and less than 1. Please use symmetry to draw graphs of exponential functions y equal to 1/3 of the power x and y equal to 1/4 of the power x. Observe the graphs and see their properties. We will still place the graphs of these two functions in the same Cartesian coordinate system. Please explore their properties. We found that the locality of both functions is in the R range, and the monotonicity between 0 and positive infinity is a decreasing function. These two functions also have the same properties as function y, which is equal to half the power of x. At the same time, we found that point O1 is also a common point between these two functions. So 0 and 1 are the common points of these four functions, right? Okay, everyone. So far, we have created a total of 6 graphs of exponential functions. I will place the graphs of these 6 exponential functions in the same Cartesian coordinate system. Please observe their images, observe their positions, common points, and trends of change, and see what commonalities they have. Please describe these properties from the perspective of graphic language. The graphs of these functions all pass through fixed point 0, 1, and their domains are in an open order from negative infinity to positive infinity. The range of values is between 0 and positive infinity in open order. When a is greater than 0 and less than 1, the graph of the function shows a decreasing state, and the function is a decreasing function. When a is greater than 1, the function graph shows an upward trend, and the function is an increasing function. These functions do not have parity. Can we derive a general exponential function graph based on the graphs and properties of the 6 functions we are exploring? Can the properties we obtain be generalized to the properties of general exponential functions? How can we ensure the reliability of the conclusions we obtain? Because there are infinitely many values for the base number a, and the accuracy obtained using the dot tracing method is still insufficient. I drew the graph of the exponential function using a geometric drawing board. Let's first look at the type where a is greater than 0 and less than 1. I usually change the value of a. Please observe the graph of the exponential function. You will find that the graph of the exponential function is always above the x-axis. Then let's take a look at the type where a is greater than 1. Similarly, observe the changes in the function graph. Please summarize their properties based on the images and fill in the summarized properties in the table below. In the table, I still divide exponential functions into 2 categories for research. One is the case where a is greater than 0 and less than 1, and the other is the case where a is greater than 1. Please write down the graph and properties of the exponential function you are studying. Let's first look at the type where a is greater than or less than 1. When a is greater than 0 and less than 1, the graph of the exponential function decreases from left to right. Its definition is that for all real numbers r, the range of values is from 0 to the positive finite open interval. Regardless of when a is taken, when the graph of the function passes through one of the fixed points x and becomes 0, y is equal to 1. The monotonicity of a function is reduced by a function. Okay, let's take a look at the type where a is greater than 1. When a is greater than 1, the graph of the function rises from left to right. The domain of the function is R, and the range of values is an open interval from 0 to positive infinity. No matter what value a takes, when the function passes through a fixed point of 0, 1, x equals 0, and y equals 1. Monotonicity is an increasing function, and functions do not have parity. Based on the table summarized by everyone, let's take a look at the commonality of exponential functions when a is greater than 0 and not equal to 1. We found that regardless of the value of a, the domain of the exponential function is an open interval from 0 to positively finite r, and their graphs pass through fixed points 0 and 1. The difference between these two types of functions is mainly reflected in their monotonicity. When a is greater than 0 and less than 1, the exponential function is a decreasing function. When a is greater than 1, the exponential function is an increasing function. On the contrary, when the exponential function is a decreasing function, a is greater than 0 and less than 1, and when the exponential function is an increasing function, a is greater than 1. This is the graph and properties of the exponential function that we are going to study in this class. At the end of this lesson, let's review the content learned in this class. Please think about the following questions. What knowledge did you learn in this class? What methods have you used in studying the graphs and properties of exponential functions? I hope everyone has not only learned mathematical knowledge in this class, but also mastered the methods of learning mathematical knowledge. Goodbye, everyone.